Hi everyone, it's Mrs. Westmoreland, and this is a video lecture for AP Chemistry on Bohr calculations. So, the interaction of electromagnetic waves, or light, with matter is a powerful means to probe the structure of atoms and molecules, and also to measure their concentration. So one way in which we did this was last semester in two of our labs. We did the Beer's Law lab and the kinetics of crystal violet fading lab, where we used the colorimeter to measure the amount of visible light absorbed by a solution and related it to the concentration of the solution. So the Beer-Lambert law formula, as well as the definition of each of the variables, is on your formula chart. And essentially what we have is the absorbance that is measured by the colorimeter being proportional to the concentration, and therefore we can make a graph of concentration on the x-axis and absorbance on the y-axis and see that relationship for a particular colored solution. There's also an interaction between infrared radiation and matter, and mostly if we bombard matter with infrared radiation, what's going to happen is that the molecules are going to vibrate and stretch, and each one of a particular type of bond will have sort of a characteristic absorbance due to its vibration and stretching of the bond. You won't have to interpret this data, but you just sort of need to know that that is the interaction of infrared radiation, is that it's about vibration and stretching of bonds. But the most important one that you'll actually have to apply is the ultraviolet and visible light that was used by Niels Bohr as evidence to justify his shell model of the atom when he absorbed the emission spectrum of hydrogen. So to understand that data of Niels Bohr, we need to understand the electromagnetic spectrum, which is pictured here. So all of these types of radiation are called electromagnetic radiation, including the small portion of the spectrum that is visible to our human eyes. And so the wavelengths that are used to describe electromagnetic radiation, because they are waves, is wavelength, which is a length, symbolized by the Greek letter lambda, and would be the distance between two crests of the wave. Frequency, which is symbolized in chemistry by the Greek letter nu, which is the number of cycles per second that pass a certain point in space, and velocity of the wave, which for electromagnetic radiation has a specific symbol, which is the letter c. So it's called the speed of light, but really it's the speed of all electromagnetic radiation. And on your formula chart, it's listed as 2.998 times 10 to the 8th meters per second. So you can see that because the wavelength and the frequency multiply together to equal a constant, as one goes up, the other goes down. They are inversely proportional. So as wavelength is large, the frequency is small, and vice versa. So Bohr's experimental evidence involved observing the emission spectrum of hydrogen. So he saw these distinct bands of energy being emitted from the atoms of hydrogen when they were excited by energy, external energy. And he concluded from there that because he saw very specific wavelengths, that they had to correspond to very specific energy levels, or transitions in energy levels, which is how he came up with his shell model. So he studied the atomic emissions for spectrum for hydrogen, and he looked at how that could relate to the structure of the atom. So he proposed that the electrons can only have specific energy level values, and that the electrons are jumping to higher energy levels when they absorb a photon of light from an external source that was of a specific value. So we cause the electrons to jump to higher energy levels, which are called excited states, when we supply them with energy. This could be in a Bunsen burner flame or in a spectrum tube, like an elemental lamp, many different ways to excite electrons. At some point, the electrons are going to lose that excess energy and fall back to their lower ground state energy level. And as they return to their ground state, energy is emitted, and that is what results in the colored bands that appear on the emission spectrum. So because each colored line represents a transition between a particular pair of energy levels, we can calculate the energy that's required for that energy transition. So here are some equations on your formula chart and calculations that can be done that's related to that evidence. And as an example, we're going to calculate the energy emitted to create the band that is measured at 410.2 nanometers on the hydrogen spectrum. So the energy wavelength, or the band's wavelength, is measured in nanometers, but the speed of light is measured in meters per second. So the first thing we have to do with our wavelength in nanometers is we have to convert it into meters by dividing by 10 to the minus 9, 10 to the positive 9, excuse me. 1 billion nanometers in 1 meter. So once we have that wavelength in meters, we can then solve the equation C equals lambda times nu and solve for frequency by dividing the speed of light by the wavelength to get the frequency. So when I do that, I get 7.309 times 10 to the 14th per seconds. So that's kind of a funky unit for frequency, sometimes referred to as hertz, but it's the number of waves that pass a certain point in space in a certain amount of time, in this case per second. And then finally, once we have the frequency, we can then use the second equation and solve for the energy of that transition, multiplying what's known as Planck's constant, also on your formula chart, by the frequency to get the energy in joules. So we're multiplying a constant of joules per second by the per seconds, and so we get the energy of that transition, of that photon that was absorbed and therefore released when we return to the ground state for that particular transition that made that particular violet colored band. So what I'd like you to do is I'd like you to calculate the other wavelength, 656.3 nanometers, which would be the red line that appears in the hydrogen spectrum, and then look at your answer to the one that I just did and the one that you do and sort of mathematically see the relationship between wavelength and energy. So you do have to convert between nanometers and meters in this calculation because you need to match up your units. So what's next? Well, what happened was that these calculations and others that were done by Niels Bohr work great for hydrogen, which only has 1 electron, but sort of start to fall apart as you get more electrons in more shells. So the Bohr model gives us an important feature, so an important step forward from Rutherford, who didn't really specify anything about where the electrons were, to Bohr, where we knew that they are in these particular shells of energy. But we need further refinements on this model. So we will continue on to another activity where we will use ionization energy data to justify shells and subshells. Thanks for listening. See you in class.